Now we're going to chapter 3, the geometric formulation of relativity. We already talked about how uh, Lorenz have this dynamic ether theory that arrived at Lorenz transformation. Compared with Einstein's with new kinematics, and Einstein's approach is enormous simplification compared with Lorenz's. And not only that, it goes beyond electromagnetism because new kinematic is really for all physics. Now we're going to show the Minkowski formulation, the geometric formulation of relativity is even simpler than Einstein's original formula. It not only that, it goes beyond special relativity, allows you to go general relativity. In fact, you cannot really allow Einstein to go to general without this geometric formulation. Minkowski's message is basically saying this. He said the key point of special relativity is that space and time should be treated on equal footing. Time, just like space, is coordinate dependent. It's just one of the So the best way to bring about this symmetry between space and time is to unite them in a single mathematical structure, which is what he calls space-time, which is space, four-dimensional space with time being the fourth dimension. Just like we like to display the equal footing of the three dimensions of physical space by viewing the x, y, z as the components of a three-dimensional vector, and they can be transformed into each other under rotations with invariance of some length, like x squared, y squared, z squared. So now, Minkowski, we should now work with a four-dimensional world with CT, x, y, z as components of 4D vector, so they can be transformed into each other by rotations. And what's kept invariant is the length, this s, this minus c squared t squared plus x squared plus y squared z squared. Okay. And of course, we'll see that the Lorenz transformation can be viewed as a rotation in this four-dimensional space-time. These are the opening words of an address that Minkowski gave in 1908 in a scientific meeting in Cologne, Germany. He said, "The views of space and time which I wish to lay before you have sprung from the soil of experimental physics. There lies its strength. They are radical. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two would preserve an independent reality." Uh, Actually, I probably should mention Minkowski was the math professor of Einstein at ETH, and in fact, Minkowski originally didn't think very much of Einstein as a student, and also Einstein didn't think, for example, this Minkowski formulation very much. He think it just learned unnecessary learnness. Uh, uh, but in a few years' time, when he worked on general relativity, then he realized this geometric formulation was absolutely crucial for his extension. And unfortunately, Minkowski died very shortly after this 1908 meeting, and I believe it was appendicitis. Anyway, so now we talk about Lorenz transformation as a rotation in four-dimensional space-time. To see clearly this rotation, let's first imagine that's the imaginary coordinates w, which is defined to be I times ct. So therefore, the invariant interval now can be written as plus w squared plus x squared y squared z squared. So just like an ordinary Euclidean length in this case, four dimension, but it's just Euclidean length. So let's concentrate on the non-trivial part, time and x components. And so therefore, if it's a rotation, among W and X is simply just the usual rotation matrix. Okay, so with some now after written this down, then we put back the WICT, then the relation between CT prime and X prime into CTX is given by this. In particular, you notice that you have this I factor here, and also we don't know what this theta is. Okay. Now we reparameterize this rotation angle theta into minus I psi, and using the identity that cosine I psi is equal to cos psi, and I times sine minus I psi equal to sinh psi. Okay, now this is in case you don't remember these hyperbolic angle relations. Just remember, all came from Euler's formula: e to the I theta equal to cosine theta plus I sine theta. So therefore, cosine can be written e to the minus I theta plus e to the I theta divided by 2. And if you substitute theta by I psi, and this relation becomes this, and this is what we call cos psi. So it's all just came from, and remember the definition of cos and sinh in terms. It's just linear combination of exponential factors. So therefore, once you substitute this in, so therefore t prime x prime in terms of t and x is in terms of these hyperbolical functions, and psi is in fact we call rapidity. Now the question is this the Lorenz transformation? And of course we need to know, obviously this psi somehow relates to relative velocity. So what's the relation? So we need to find out whether this is really Lorenz transformation by finding the relation between psi to the relative velocity v. So now we're going to look at this rotation. And so now we try to relate this psi to the relative velocity v. Now we have two frames, O frames in blue and O prime frame in red. Red is moving with a v in the x direction. Okay. So the particular, let's concentrate on the x prime equals 0, the origin of the O prime system, which is moving in the O frame with v. So therefore, this distance here is vt. Of course, we're assuming that two coincide at t equals 0. So therefore, x prime equals 0, according to this way, is x prime is written as minus ct's sinh psi times x times cos psi. So that's equal to 0 for the, and so therefore the ratio, if this equals 0, the ratio of x over ct simply is sinh over cos, or hyperbolic tangent psi. So that's the relation between psi and x over t, of course, is v. X equals vt, so therefore x over ct is v over c. So the relation between the rapidity psi and v is this relation: hyperbolic tangent of psi equal to v over c, which we call beta. Now, of course, the Lorenz transformation elements are in terms cos and sinh, not in terms hyperbolic tangent. So now remember the relation between cos squared minus sinh squared to 1. And then we can write this by taking the square root is cos psi equal to 1 minus 10 sinh over cos, so hyperbolic tangent square, and that's equal to 1. Okay. So therefore, the cos psi is equal to, because this is beta, so this is 1 over beta square, and that simply is gamma. So the cos psi is simply equal to the Lorenz gamma factor, and sinh equal to gamma beta. So therefore, this matrix can be written as gamma over, take out the gamma factor, 1 minus beta. That's exactly the Lorenz transformation we had before. So therefore, Lorenz transformation really is a rotation, okay? But of course, in this funny coordinate system. That's funny because the length you want to keep to be the length is actually have this funny minus sign of c in front of c squared t squared. So that's the end of the second part of the third lecture.